Low voltage protection is essential for electrical safety in both industrial and commercial settings. Several types of protection devices are used to safeguard equipment and personnel. Firstly, overcurrent protection is a fundamental aspect. Fuses are sacrificial devices that break the circuit when the current exceeds a predetermined value. They are a one-time use item and must be replaced after they blow. Circuit breakers are resettable devices that automatically trip when the current exceeds a set threshold. These can be reset after the fault is cleared, making them more convenient than fuses in many applications. Secondly, short-circuit protection is crucial. Short-circuit interrupters, or GFCIs, are devices that detect and interrupt short circuits before they cause damage. These devices are designed to quickly isolate the faulted circuit, preventing further damage to equipment and reducing the risk of electrical fires. Thirdly, ground fault protection is necessary. Ground fault circuit interrupters, or GFCIs, are devices that detect current imbalances between the live and neutral conductors and trip the circuit if a dangerous ground fault occurs. GFCIs are commonly used in wet locations, such as bathrooms and kitchens, to protect against electric shock. Fourthly, surge protection is important to consider. Surge protectors are devices that divert excess voltage surges away from sensitive equipment. These surges can be caused by lightning strikes, power grid switching, or other electrical disturbances. Surge protectors help prevent damage to electronic devices and appliances. Fifthly, arc fault protection is also vital. Arc fault circuit interrupters, or GFCIs, are devices that detect hazardous electrical arcs and trip the circuit to prevent electrical fires. Arcing faults can occur due to damaged wiring, loose connections, or other insulation failures. GFCIs are designed to detect these arcs and quickly de-energize the circuit, reducing the risk of fire. Different types of loads are present in industrial and commercial buildings. In industrial settings, typical loads include motors such as induction and synchronous motors, which are used to power machinery and equipment. Heating elements are used for various industrial processes, such as heating liquids or materials. Lighting fixtures provide illumination for the workspace. Transformers are used to step down voltage levels for different equipment. Computers and electronic equipment are essential for controlling and monitoring industrial processes. In commercial buildings, common loads include lighting fixtures that provide illumination for offices, retail spaces, and other areas. Heating, ventilation, and air conditioning systems, or HVAC systems, regulate temperature and air quality in the building. Elevators transport people between floors. Fire alarm and security systems protect the building and its occupants in case of emergencies. Office equipment, such as computers and printers, are used for day-to-day business operations. Selecting the appropriate protection devices depends on several factors. Firstly, load current and voltage must be considered. The protection devices must be rated to handle the expected current and voltage levels of the load. Secondly, the type of equipment being protected must be taken into account. Different types of equipment have different protection requirements. Thirdly, the operating environment plays a role. Harsh environments may require more robust protection devices. Fourthly, potential hazards, such as electrical fires and short circuits, must be considered. The protection devices should be selected to mitigate these risks. Additional tips to keep in mind include, firstly, using properly sized and rated protection devices. It is crucial to select devices that are appropriate for the specific application. Secondly, following proper installation instructions. Incorrect installation can compromise the effectiveness of the protection devices. Thirdly, regularly inspecting and testing protection devices to ensure they are functioning properly. This helps identify potential problems before they lead to equipment damage or safety hazards. Fourthly, combining multiple protection devices for enhanced safety. This can provide redundancy and ensure that the system is adequately protected. Lastly, seeking professional guidance from an electrician or electrical engineer for complex or specialized applications. These professionals can provide expert advice on selecting and installing the appropriate protection devices. The National Electrical Code, or NEC, provides guidelines for electrical installations, including the selection and installation of overcurrent protection devices. Article 240 of the NEC covers overcurrent protection. Section 240.4 addresses the protection of conductors. Conductors must be protected against overcurrent in accordance with their ampacities. The ampacity of a conductor is the maximum current in amps that it can carry continuously under specific conditions of use without exceeding its temperature rating. Table 310.15b16 in the NEC provides ampacity ratings for various types of conductors based on their insulation type and size. For example, a 12 American wire gauge or AUG copper conductor with type THHN insulation has an ampacity of 30 amps at an ambient temperature of 30 degrees Celsius. Overcurrent protection devices, such as fuses and circuit breakers, must be selected with an ampacity rating that does not exceed the conductor's ampacity. Section 240.6 of the NEC lists the standard ampere ratings for fuses and circuit breakers. These standard ratings are typically available in increments of 15, 20, 25, 30, 35, 40, 45, 50, 60, 70, 80, 90, 100, 110, 125, 150, 175, 200, 225, 250, 300, 350, 400, 450, 500, 600, 700, 800, 1000, 1200, 1600, 2000, 2500, 3000, 4000, 5000, and 6000 amps. When selecting an overcurrent protection device, it's important to choose a standard rating that is closest to, but not exceeding, the conductor's ampacity. For example, if a 12 AWG copper conductor with type THHN insulation is used, which has an ampacity of 30 amps, a 30 amp fuse or circuit breaker would be the appropriate choice. Section 240.4d provides specific requirements for the overcurrent protection of small conductors. For example, 14 AWG copper conductors must be protected by a 15 amp overcurrent protection device, and 12 AWG copper conductors must be protected by a 20 amp overcurrent protection device, unless specific exceptions apply. Article 430 of the NEC covers the protection of motors and motor circuits. Motors require specific overcurrent protection to prevent damage from overloads and short circuits. Section 430.52 provides guidelines for selecting the motor branch circuit, short circuit, and ground fault protective devices. The type of motor and its full load current rating are important factors in determining the appropriate protection. For example, for a motor with a full load current of 20 amps, the maximum rating of the short circuit and ground fault protective device depends on the type of motor and the type of protective device. For an inverse time circuit breaker, the maximum rating is typically 250% of the motor's full load current. For an instantaneous trip circuit breaker, the maximum rating is typically 800% to 1300% of the motor's full load current, depending on the motor's design. For a dual element fuse, the maximum rating is typically 175% of the motor's full load current. Section 430.32 provides requirements for motor overload protection. Motor overload protection is designed to protect the motor from overheating due to prolonged overloads. Overload protection can be provided by overload relays, which are typically part of the motor starter. The overload relay is selected based on the motor's full load current and service factor. Article 440 of the NEC covers the protection of air conditioning and refrigeration equipment. Air conditioning and refrigeration equipment have specific protection requirements due to the presence of compressors and other specialized components. Section 440.22 provides requirements for the rating and selection of disconnecting means and branch circuit overcurrent protection for air conditioning and refrigeration equipment. The disconnecting means must be capable of disconnecting the equipment under load. The branch circuit overcurrent protection must protect the equipment from short circuits and ground faults. Section 440.12 provides requirements for motor compressor overload protection. Motor compressor overload protection is designed to protect the compressor motor from overheating due to prolonged overloads. Overload protection can be provided by overload relays or other thermal protection devices. Article 500 of the NEC covers the classification of locations for electrical equipment and wiring in hazardous, or classified, locations. Hazardous locations are areas where flammable gases, vapors, dust, or fibers may be present in sufficient quantities to cause a fire or explosion. The electrical equipment installed in hazardous locations must be specifically designed and approved for use in those locations. Hazardous locations are classified into different classes, divisions, and zones based on the type and likelihood of the presence of hazardous materials. Class I locations are those in which flammable gases or vapors may be present in the air in quantities sufficient to produce explosive or ignitable mixtures. Class II locations are those in which combustible dust is or may be present in the air in quantities sufficient to cause a fire or explosion. Class III locations are those in which easily ignitable fibers or materials producing combustible flames are handled, manufactured, or used. Divisions indicate the probability of the presence of hazardous materials. Division I locations are those in which hazardous materials are present continuously, intermittently, or periodically under normal operating conditions. Division II locations are those in which hazardous materials are not normally present but may be present accidentally. Zones are used in place of divisions in some hazardous location classifications. Zone 0 locations are those in which hazardous materials are present continuously for long periods. Zone 1 locations are those in which hazardous materials are likely to exist under normal operating conditions. Zone 2 locations are those in which hazardous materials are not likely to exist under normal operating conditions. Electrical equipment installed in hazardous locations must be marked to indicate the class, division, or zone for which it is approved. The equipment must also be designed and constructed to prevent ignition of the hazardous materials. Different types of protection techniques are used for electrical equipment in hazardous locations, including explosion-proof enclosures, intrinsically safe circuits, and purged and pressurized enclosures. Explosion-proof enclosures are designed to contain an internal explosion without allowing the explosion to propagate to the surrounding atmosphere. Intrinsically safe circuits are designed to limit the energy available in the circuit to a level that is too low to ignite the hazardous materials. Purged and pressurized enclosures are designed to maintain a positive pressure of clean air or inert gas inside the enclosure to prevent the entry of hazardous materials. Grounding is an essential safety practice in electrical systems. Grounding provides a low-impedance path for fault current to flow back to the source, allowing overcurrent protection devices to quickly trip and clear the fault. Proper grounding helps prevent electric shock and reduces the risk of fire. Article 250 of the NEC covers grounding and bonding requirements. Grounding systems typically consist of a grounding electrode, a grounding electrode conductor, and equipment grounding conductors. The grounding electrode is a conductor that is buried in the earth and provides a connection to ground. Common types of grounding electrodes include ground rods, ground plates, and metal underground water pipes. The grounding electrode conductor connects the grounding electrode to the electrical system's neutral point, such as the neutral bus in a service panel. Equipment grounding conductors provide a lower impedance path for fault current to flow back to the source from non-current carrying metal parts of electrical equipment. Equipment grounding conductors are typically run with the circuit conductors and are connected to the equipment enclosure and other metal parts. Bonding is the process of connecting together all non-current carrying metal parts of an electrical system to create a low impedance path for fault current. Bonding helps to ensure that all metal parts are at the same electrical potential, reducing the risk of electric shock. Bonding jumpers are used to connect together metal raceways, enclosures, and other metal parts. Surge protection devices, or SPDs, are used to protect electrical equipment from voltage surges. Voltage surges can be caused by lightning strikes, power grid switching, or other electrical disturbances. SPD divert excess voltage away from sensitive equipment, preventing damage. Article 280 of the NEC covers surge protection devices. SPD are typically installed at the service entrance of a building to protect the entire electrical system. SPD can also be installed at the branch circuit level to protect individual equipment. SPD are rated based on their ability to withstand voltage surges and their let-through voltage, which is the maximum voltage that will be allowed to pass through the SPD. Different types of SPD are available, including metal oxide varistors, or MOS, and silicon avalanche diodes, or SADs. MOV are the most common type of SPD. They are relatively inexpensive and can handle large surge currents. SAD are more expensive than MOV but offer faster response times and lower let-through voltages. Arc fault circuit interrupters, or GFCIs, are devices that detect hazardous electrical arcs and trip the circuit to prevent electrical fires. Arcing faults can occur due to damaged wiring, loose connections, or other insulation failures. GFCIs are designed to detect these arcs and quickly de-energize the circuit, reducing the risk of fire. Article 210.12 of the NEC requires GFCIs to be installed in dwelling units to protect branch circuits that supply receptacles, lighting, and other loads. GFCIs are designed to detect different types of arcing faults, including series arcs and parallel arcs. Series arcs occur in a single conductor, such as a broken wire. Parallel arcs occur between two conductors, such as a wire and a ground. GFCIs use sophisticated electronic circuitry to distinguish between normal arcing, such as that caused by a switch opening, and hazardous arcing faults. Ground fault circuit interrupters, or GFCIs, are devices that detect current imbalances between the live and neutral conductors and trip the circuit if a dangerous ground fault occurs. GFCIs are commonly used in wet locations, such as bathrooms and kitchens, to protect against electric shock. Article 210.8 of the NEC requires GFCIs to be installed in dwelling units in bathrooms, kitchens, garages, outdoors, and other locations where there is a high risk of electric shock. GFCIs work by monitoring the current flowing through the live and neutral conductors. If there is a difference of 5 mA or more between the two currents, the GFCI will trip and de-energize the circuit. This indicates that current is leaking to ground, which could be a sign of a dangerous ground fault. GFCIs are available in different types, including receptacle-type GFCIs and circuit breaker-type GFCIs. Receptacle-type GFCIs are installed in place of standard receptacles and provide GFCI protection to the receptacle and any downstream receptacles. Circuit breaker-type GFCIs are installed in the service panel and provide GFCI protection to the entire branch circuit. Electrical safety is of paramount importance in both industrial and commercial settings. By understanding the different types of low-voltage protection methods and selecting the appropriate devices for specific applications, you can help ensure the safety of equipment and personnel. Always follow the National Electrical Code and seek professional guidance from an electrician or electrical engineer for complex or specialized applications. Regular inspection and testing of electrical systems are also crucial for maintaining a safe electrical environment. Be sure to properly maintain electrical equipment to ensure safety and proper operation.